Okay, since we found the critical points, we need to figure out whether they are mins or maxes. And while we're at it, we'll also find concavity up and down. These critical points are t-values. So it's going to be drawing a chart, but I'll need to find x and y at some point if I want to draw this. But there's t equals -1, 0, and 1, the three critical numbers. And I'm going to skip finding increasing, decreasing for t's. You could do that, but instead I want to go straight for the second derivative test and find concavity. That's one of the best ways to draw these pictures. So the second derivative, d squared y dx squared, we found that on the previous page. It's 3t squared plus 1 divided by 4t cubed. And then if you plug in -1, where the derivative was equal to 0, you get 3 times t squared plus 1, so you get 6 on top, and on bottom you get -4, so that's less than 0. And so that means it's a maximum. If it's less than 0, that's concave up, so it's a max. I'm sorry, I said that concave down, so it's a max. Right. Let's go ahead and see what that picture looks like so I can make the point. At t equals -1, there's the top of the curve, and I needed to know where that was on the curve. It's if I plug in t equals -1 to the original function, I get the point 1, 2. That was the original function from the previous page. So I plot a point there, and I say concave down because the second derivative is less than 0. Alright, so looking over here at t equals 1, if I plug that into the second derivative, I get a number greater than 0. This time it'll be 6/4. So that means concave up, which is a minimum. So there's t equals 1. If I look at the point t equals 1, xy will be 1, -2. So I draw those 2 points, and I went ahead and plotted the point at t equals 0. That turned out to be 0, 0. And remember, that was where the derivative was vertical. So that's a derivative doesn't exist there, but it means it's a straight up and down tangent line. So far I have a rough sketch. I know t equals 1, 0, and -1, so I could draw arrows going from lesser t to greater t. And I know it's concave up everywhere for t greater than 0, and concave down for everywhere t less than 0. So it's got to look basically like that. And then there's that point, an interesting point where it crosses. I could figure that out. I could just set y equal to 0 and find the two values where t is equal to 0. So if I set t cubed minus 3t is equal to 0, and then I factor the t, then I get t is equal to 0, or t is equal to plus or minus square root of 3. So that's the t values. So t is equal to 0 I already plotted, and plus or minus square root of 3, that's either a little bit smaller than -1 or a little bit bigger than +1. That's where those two lines cross. So this does a loop. That was the original function. And one more new topic that I'll mention on this video is the arc length. Let's just define it. The arc length is when you have a parameterized curve and you would like to figure out how long that curve is from point t equals a all the way to the point t equals b. So the basic scheme is that you chop it up into small pieces and measure straight lines. And the straight lines will be little secants that cut it off, and they can always make them into a little right triangle, and the distances on the left, on the bottom and the side of it are dx dt and dy dt. So you can make the length to be the integral from a to b of the Pythagorean theorem, the square root of dx dt squared plus dy dt squared. Then times dt, because you have to multiply by time to get length, to get the total length there to come out. Well, just integrate it with respect to t. And if you look at that dt on the outside, it really does cancel out with the dt on the inside. but and you could just see it as dx squared plus dy squared, which would be the actual real lengths that we'd be interested in squaring and taking the square root. So we really just inserted the dt in the denominator and the outside. But that's the formula. The length of the arc from a to b, square root dx dt, dy dt, both squared, added together. A lot of times it's impossible to find that integral, and so mostly we just need to be able to set it up. So here's an example of setting up the arc length for curve C, x equals e to the t, y equals sine 7t, for t element of negative 2 to 5. So it's the integral from negative 2 to 5, same end point and start point for t. Take the two derivatives. E to the t is its own derivative, square it, and derivative of sine 7t is 7 cosine 7t, square that. And now you have the setup, and that's all that you needed to do. Now, if you want to find the arc length of a function, y equals e to the 3x plus x squared from x equals 1 to 5, then there's a two-step process. First, you can force it to be parameterized. So this is the way to do that. All you have to do is let x equal to t, and then y is just equal to the same function that you started with, but t in for x, e to the 3t plus t squared. And then t goes over the same values that x does, because x is equal to t. So t goes from 1 to 5. And then using the formula that we have, looks like 1 to 5. The derivative of x with respect to t will always just be a 1. And the derivative of y with respect to t will be something you can find there. And we square them both, and then dt. And you notice that's the same formula for arc length as you would have seen earlier in the book for the arc length of a function of x. So the parameterized arc length is really the more general one. It lets you do it the same thing to x and to y.